the first of a series of lectures covering the concept of function. The concept of function in mathematics is extremely basic, and it is fundamental in order to understand almost anything in mathematics. The term function, or also map, lies at the foundation of mathematics. Given two sets x and y, a function, loosely speaking, is a way or a criteria or a relation to associate one element of y to each element of x. This very common phrasing is a bit of hands waving mathematically, since the words in quotes have not been defined at this point. The association of elements of x to elements of y usually is indicated in the following way. So we first write x on the left, and then we write an arrow pointing right bound, and then we write y on the right. Typically, we can give a name to this function, for example, f. In that case, we can write f here with the colon, or else we can write it up here over the arrow. This will indicate graphically that to each element of x, f will give a criteria to associate an element of y. Let's now give a formal mathematical definition of function. In order to do that, we have to first introduce a more basic concept than a function, the so-called relation. Here is the mathematical definition of function. Definition: a relation between two sets, x and y, in this order, is a subset R of the Cartesian product x cross y. And to see what the definition of Cartesian product and a short discussion of it, I refer you to the lecture 1.1. Now let's suppose that R is a relation between x and y. Then, so x is going to be the domain of R, and y is going to be called the codomain of R. That being said, if A in x is related to B in y, we write A related to B. What does it mean, an element of A in x related to B in y? It means that the pair A, B in the Cartesian product x times y is in R. Okay, R is a subset of the Cartesian product of x times y. So every element is an element of x, an element of y. And every time we have an element in R of the kind A, B, we will say that A is related to B, and we will write A, R, B. Now, definition number one, let f be in the Cartesian product x cross y be a relation. Then f is a function from x to y if the following two conditions are satisfied. The first one being that for any element A of x in the domain, there exists a B in y such that A f B, so such that A is related to B according to this previous notation. And then the second condition is if A is related to B1 through f, and A is related to B2 through f, then B1 equals to B2. So this is a way of saying that A can be related through f just to a unique element of y. There will be just one element of y that will be related to A. What does this mean in terms of the hands waving definition that we mentioned before? So if we write f as such, so x, arrow, y, Condition A simply means that for every element of x, let's call it A, I will have an image here called f of A, right? So this is a typical notation to say that f of A is related to A in terms of the hands-waving definition, which is the most commonly used one, by the way, and it is the one we will certainly use in the series of lectures. So there will not be an element of x which will not have an image in y. Every element of x will have an image in y. Condition B simply means that to each element of x, A, there will be a unique element in y related to A. So every element of x is related to an element of y, but can be related to just a unique element of y, not two elements of y simultaneously. Let's now say a few words about the correspondence between the hands-waving definition and the mathematical definition that we have just given of a function. Let f be a hands-waving function, meaning that we represent f as a law, a correspondence between two sets, x and y. We associate to f its graph. Definition number 2, the graph of f, denoted as an arrow from x to y, is the subset of the Cartesian product of x times y, which is going to be a relation, of course, because any subset of the Cartesian product is a relation. So is the subset of x cross y, given by the following definition. Graph of f are the pairs a, comma, f of A. So when A ranges inside x, this pair of points, of elements, a, comma, f of A, will be in x times y. Because f of A, by definition, is an element of y, is the unique element of y that is associated to A through the hands-waving function f. It is easy to see the graph of f is a function, according to definition number 1. If we assume, of course, f to have the previous two properties that we have listed, namely that to each element of x there is a corresponding element in y, and this element associated to x is unique. There cannot be two of them. Vice versa, let R in x cross y be a relation that is a function. Now, how do we associate to that a correspondence between x and y? A law that allows me to associate to any element of x an element of y. So let R be the set of points, of elements of the kind Rx and Ry. Okay, so I explicited R as a subset of xy by means of the two elements that represent every element in R. Now we define a hands-waving function for f from x to y in the following way. We take R of x, which of course is an element of x, since R of x, R of y is an element of x Cartesian product with y, and we associate to R of Rx the element Ry. So we take the first element here on the left and we associate to it the second element here on the right. By property A of definition 1, for each A in x, there exists R of x, which is exactly equal to A. Okay, since R is a function, then for every element of x, there is an element of R which has that element as a first element here in this pair. So every element A in X has an image, namely the other element, the second element here in this pair. Moreover, this image is unique by property B of the relations in order to be functions. So for the time being, by function, we will denote hands-waving notion, and the associated relation will be its graph. So what we have just seen now is that to have any hands-waving function, we have associated a mathematical function, which we will call graph, and to any mathematical function, we can associate a hands-waving function. Therefore, these notions are equivalent one to the other. But the way we will write functions normally will be like hands-waving functions. And the mathematical function associated to it will be denoted by the graph of the hands-waving function. Let's see now 3 examples of functions and relations and see graphically what the 2 conditions that make a relation a function amount to. So for drawing purposes, we represent x and y like a line each. Okay, so we have here x, a horizontal line, y is a vertical line, and the Cartesian product between x and y will be looking like the Euclidean plane. Okay, so all these points in this black area are the points that correspond to the Cartesian product between x and y. So let's draw 3 relations between x and y. So 3 subsets inside this cross product, this Cartesian product. We will denote them by R, F, and S, and draw them according to the colors that we have introduced here. Let's start off with R. So suppose that this is R. So this is a relation. At this point, since it's just a subset of x and y, then we will discuss if it has further properties or it's just a relation. For the moment, each of them will be a relation. F is the following, and S is this one. Now, for the moment, let me just delete F and S, and let's concentrate on R. So R, we can see right away that is not a function because of failure of property B. What property B stated? Property B stated that to each element of x, there should be a unique element of y, which is in relation with that element of x. We take this element of x, which we call x1. It is this element here, right here. We can easily see that there are 3 points associated to 3 elements of y associated to x1, namely the intersection point of this vertical line here, parallel to y, let's say, passing through x1. So there will be an y1 down here, and then a y2, and then a y3. So that breaks the condition that to each x1 there should be a unique point, a unique element in y related to it. Okay. So the element x1, for instance, is related to 3 different points of y, namely those denoted y1, y2, and y3 in the picture. Let's focus now on the relation S that we have drawn here. Notice that the element of x that are related to some element of y, they are actually related to a unique element of y. Indeed, if you take any element of x here above the relation S, and you go to intersect it to S, you will find just a unique element of y related to such element of x. But property A for a relation to be a function is not satisfied, because there are elements of x that are not related to any element of y. For example, here, if I take an element of x here, this is not related to any element of y through the relation S. Therefore, once again, S is not a function because of failure of property A.